Welcome back to our course. We have a beam DB with vertical cantilevers, one at D of length 2 meters and the other heading downwards at C with length 2 meters. To move these 4 tons at D, we move it with a load of 4 tons in the same direction and a moment rotating about D in the same sense of the load. So we have at D 4 tons of the same magnitude and direction of the given load and a moment 4 by 2. 4 by 2 rotating counterclockwise. Similarly at C, we compensate for these 2 tons by a force at C in the same direction and magnitude of the given load and a moment rotating about C in the same sense of the rotation of these 2 applied tons. So we have our 2 by 2 equals 4 meter tons here. To get our problem ready for the computation of reactions, we have to get a resultant of the distributed load between C and B. The resultant is the intensity of the load, 1, by the length on which the load is applied, 6 meters. The resultant 1 by 6 is acting in the middle of CB. We determine our reactions. We have one reaction YA at A and 2 reactions Y and X at B, as B is a hinge. Our first equation of equilibrium will be moments about B equals 0. So the first load is 1 by 6, and the first moment due to this load is 1 by 6 by this distance, the arm forming the moments. So we have 1 by 6 by 3. Any moments rotating in the counterclockwise, therefore, will be positive. Any moments rotating in the opposite sense will be negative. So we have minus 2 by 2 minus YA by the arm AB 9 plus 4 by 2, which is this 8 meter tons. This gives a reaction YA equals 2.44 tons. To get YB, we apply the equilibrium equation sigma forces in the Y direction equals 0. So we have all our vertical directions, 2.44, the 1 by 6 and YB. This gives YB equals 3.56 tons. Sigma forces in the X direction equals 0. We apply all forces in the X direction. This 4 tons, 2 tons and the XB. This gives XB equals 6 tons. Now we are ready to plot our straining actions. The normal force. To plot our normal force, recall that we are searching for all forces in the direction of the center line. So we have these 4 tons, 2 tons and 6 tons XB. If you start at the end D, it is very clear that this 4 tons is a tension force and therefore will be positive and apply and plotted above the center line of the beam. Any forces in the same direction heading left and causing tension force will increase the positive normal force. Therefore, we'll head up. So we have these 4 tons heading up, and any positive normal force in the same direction will increase the positive force and will head up on the diagram. Any force in the opposite direction will decrease this positive normal force and will head down on the diagram. So we really have these 4 tons constant till we reach C. Also note that at C we expect to have 2 values of normal force, one at the left of C and the other one at the right of C. This is due to the existence of the concentrated normal 2 tons at C. The difference between the normal at C left and the normal at C right will be the value of the applied concentrated normal 2 tons. So we get our NC right equals the last value of the computed normal plus the applied 2 tons, giving 6 tons. And this 6 tons will be constant until we reach B. The closure of our diagram is by the virtue of this 6 tons XB. To plot our shear force diagram, we search for all forces perpendicular to the center line of the beam, as we explained previously. If we start from the left side, D, we will head up on the diagram with all upward forces and vice versa. If we start from the right, at B, we will inverse directions. In other words, all forces heading upwards will cause downward plots on the shear diagrams and vice versa. Also, please note that we expect to have 2 values of shear at A due to this concentrated shear force 2.44 tons. The difference between shear A left and shear A right will be the value of this concentrated force. So the value of the shear force between D and A is 0. We have no vertical forces causing shear. So QA left equals 0. But directly, QA right equals this 2.44 tons. The value of the shear is constant until we reach C. We expect to have from C to B an inclined line expressing our shear due to the distributed load, which causes a shear of the first order. And therefore, Q at B equals the last computed shear at C minus 1 by 6 gives a shear at B of minus 3.56 tons. And the closure of the shear diagram will be by the virtue of the YB 3.56 heading upwards, and we head upwards with it on the diagram. We compute our moments. The method of plotting any moment diagram is simply calculating the moments at the points of variation and then connecting each 2 adjacent moments together. So we will have a moment at D, at A, those are the points of variation, and a moment at C left, and another one at C right. We have two values at C, one at left and one at right, due to the concentrated applied moments 4 meter tons at C. Of course, we recall that a parabola will be held between C and B between the two computed moments, one at C and another at B, because a distributed load causes a second degree order moment. Please note that MB equals 0. Moment at B must equal 0 because this hinge support is located at the end of the beam, while this roller A carries a moment here because it is not located at the end of the beam. Our first moment is moment at D, which is minus 8 meters ton. This is a concentrated applied moment here. The negative value means that the tail of the moment is located above the center line of our beam and will be plotted upwards. Here we are. Moment at A will be the same value if you compute from the left-hand side, minus 8 meter tons. Let us consider the original problem to compute moments at C. So we can observe that 3 members are connected at C here. One at the left, the other at the right, and we have the vertical cantilever. Take the different sections here to be C1, C2 for the cantilever, and C3 for the left member. Moment at C1 means that we will compute our moment here from all forces on the right of the C section. So we have 3.56 multiplied by the arm 6. We have 1 multiplied by 6 by the arm 3. And please note the sign convention. YB, the moment caused by YB, has a positive sign because it causes a moment with a downward tail. Tension fibers on the lower fibers. 1 by 6 has a negative direction or a negative sign as the tail is upwards, causing the lower fibers to be compressed. And we'll simply plot this 3.36 on our notation here. To compute MC2, we simply go back to the cantilever here, and we have a moment 2 by 2 with a tail on the side shown here. Now, all sections at C must be under equilibrium. This means that the 3 moments applied at C1, C2, and C3 must have a sum of 0. And therefore, by equilibrium of this joint, we have MC3 equals the difference between these 2 moments, which gives 0.68 meter tons and heading in this direction. We will really apply on our diagram MC1 and MC3 as we excluded the cantilever. Of course, we have its effect on our diagram. We note that 3.36 plus 0.68 gives this 4 meter tons here. So MC3 will have 0.68 meter tons plotted upwards with the tail of our moment. MC1 will have 3.36 plotted downwards with the tail of the moment, and our zero moment at B. We drop our parabola W L squared over 8, which is 6 squared over 8, 4.5 meter tons here. This concludes with our problem.